Imagine the universe at the end of the 19th century, a grand, clockwork cosmos. Physicists felt they were on the verge of knowing almost everything. The laws of Isaac Newton governed the graceful dance of planets and the flight of a cannonball. James Clerk Maxwell's equations had united electricity, magnetism, and light into a single, elegant symphony of waves. It was a beautiful, orderly, and predictable universe. Scientists believed they were merely tidying up the final details, filling in the last few decimal places. It was a time of supreme confidence. They had built a magnificent cathedral of knowledge, and its foundations seemed unshakable. But in the shadows, a stubborn little problem refused to go away. This problem glowed in the dark. It came from something physicists called a black body. Think of a kiln with a tiny peephole. When you heat it up, it starts to glow, first a deep red, then a brilliant orange, and finally a dazzling white blue. The puzzle was this: the established laws of physics couldn't predict the colors of that light. When scientists tried to use their best theories to calculate the energy radiated, the math went haywire. It predicted that any hot object should be blasting out an infinite amount of energy in the ultraviolet range, an ultraviolet catastrophe. This discrepancy was a deep, dark crack appearing in the beautiful facade of 19th century physics. Enter Max Planck. In the year 1900 he was a well-respected, middle-aged professor in Berlin. He was a master of thermodynamics, the science of heat and energy. Planck was a man who deeply believed in the order and logic of the physical world. He was cautious, he was meticulous, he was deeply conservative in his scientific views. He had immense respect for Newton, he had immense respect for Maxwell. The last thing he wanted to do was to tear down that beautiful structure. His goal was to fix the crack, to patch up the problem of blackbody radiation. He saw it as a puzzle to be solved within the existing rules. Planck dedicated himself to this single, frustrating problem. He spent years wrestling with the mathematics. He was like a detective poring over the clues of a case that everyone else had given up on. The clues were the precise measurements of light emitted at different temperatures. The suspect was the universe itself, and it wasn't giving up its secrets easily. His quest was not for fame or glory, but for a return to order. After years of frustration, Planck decided to try something radical. It was a move born not of conviction, but of sheer necessity. He decided to cheat, just for a moment, to see if he could find a mathematical trick that would make the numbers work. He imagined that the energy being emitted by the blackbody wasn't a continuous flow like water from a tap. Instead, he proposed energy could only be released in tiny, discrete packets, like currency that only comes in coins of a specific value. You could have one packet of energy, or two or three, but never 1.5. He called these little energy packets Quanta. The size of each packet he proposed was tied to the frequency or color of the light. High-frequency light, blue, ultraviolet, came in big packets. Low-frequency light, red, came in smaller packets. This was a bizarre idea, but Planck's assumption had a stunning consequence. It perfectly tamed the ultraviolet catastrophe. The resulting formula matched experimental data for blackbody radiation with breathtaking precision. The quantum was born. On a cold December day in 1900, Max Planck stood before the German Physical Society in Berlin. He presented his formula, and then, almost hesitantly, he revealed the strange assumption he had used to derive it, the idea that energy comes in discrete packets, or quanta. The reaction from the audience was not a thunderous ovation. It was more like polite confusion. Most physicists likely thought it was a clever mathematical sleight of hand, not a description of how nature actually worked. For years, Planck's idea remained mostly a curiosity. 5 years later, in 1905, a young patent clerk in Switzerland, Albert Einstein, was about to have a miracle year. Einstein took Planck's idea and ran with it. Einstein made a bolder claim. Light itself is made of these packets. Light is not just a wave, light is also a particle. A particle he called the photon. He used this to explain the photoelectric effect. Suddenly, Planck's quanta weren't just math, they were real. The quantum was not just a quirk of blackbodies but a fundamental feature of the universe. The dominoes began to fall. The world that grew from Planck's tiny quanta is the world we live in today. Without quantum mechanics, the entire technological landscape of the 21st century would be unimaginable. Every single solid-state electronic device is a child of the quantum revolution. The transistors that power your computer, your smartphone, the entire internet, their operation relies on a deep understanding of how electrons behave in quantized energy levels within materials like silicon. Planck's discovery is the reason you can read these words on a screen. It gave us lasers, used in barcode scanners, used in delicate eye surgery. Every time a doctor uses an MRI machine, they are using a technology that traces its lineage directly back to Planck's struggle with a glowing piece of metal. Even our understanding of the cosmos is built on Planck's legacy. From the impossibly small to the astonishingly vast, the quantum reigns supreme. He taught us that even in the faintest glow, you can find the blueprint for the cosmos.